All right, in objective 2 here, what we have, we're trying to do what's called composition. And we've looked at composition before in terms of inverse functions. Well, composition is I'm taking a function and I'm putting it inside of another function. And I can see that's what is happening in this kind of peculiar picture. And sure, you can interpret it on multiple levels, maybe a social level or whatever, but mathematically, how I can interpret this is that it has a function within another function. For example, I have a washing machine for my clothes, and inside the washing machine for the clothes is another washing machine, which is the lady for the clothes. Yeah, so like I said, socially, you can take that how you want to. Anyway, so that's what we're doing, function composition. This happens whenever you take one function, you stick it in for x into another function, right? We've seen this before. So here's one of the notations. H of x, our new function, is equal to g of f of x. You could read it like that, where f of x, that's the interior function. It gets substituted in for x in the exterior function, which is g of x. Interior, it's on the inside, it goes in for x in the g of x function, which is the exterior one. Okay, so there's one notation. Here is another notation that means the same thing. It looks like a little O right in the middle, so it looks like it spells goff, or if I did it in the other direction, it looked like it spelled fog. But this is read as g composed with f. But you can also say g of f of x. Whichever one is closest to the x is the interior function, and that's the one that goes in for x in the exterior function, in this case g of x. Again, I'll say that again. The one closest to the x is the interior function, and that's the one you substitute in for x in the other function. Okay? Now, when I mentioned that the domain thing might be tricky, here it is. So this is how the domain works. Since you're taking a function and you're sticking it into another function, one domain, like the domain of the interior, it has an output. The output now becomes the input in the other function. Do you see what I'm saying? Right? Okay. So in function composition, the domain of your new function, h of x, is the set of all x's in the interior function. In this case, this is f of x, such that f of x, that's its range, is in the domain of g of x. Whew. Let's look at that in some diagrams. Okay, so I have an x value that is inside the original f of x. Okay, it's going to output into something that's in that red circle there, its range. I only get to use those numbers that are also in the domain of the exterior function, g of x. And then whatever I get, it gets outputted into g of x's range. Okay? So I may not get to use every single thing that's in the blue thing. I only get to use the part of it whose output is also in the green part that's down there. That's a lot to take in. Okay, so in other words, we can only use x values that are in the domain of the interior function, the f of x1 in this case, if its range, if its output is also in the domain of the exterior function. That's the best way to think of it. Okay, and here's a simplified case. Here's a simplified case that, in other words, the domain of your composition, h, is going to be exactly the same as the domain of the interior function, which is f of x in this case, as long as its range is completely inside, watch that, completely inside the domain of the exterior function. Sometimes that happens. It always happens if it's all real numbers. That's the simplest case. But it doesn't always happen. So let's see if we can handle some of this. All right, are you up to it? Exercise 4 is just straightforward, not working with the functions too much, just with the number parts. Okay, let f of x equal 3x minus 14, g of x equal x squared plus 5. What we're trying to find is g of f of 4, or g composed with f of 4. So in order to do this, essentially you want to work from the inside. You want to first find the f of 4. Whatever I get, let's call it k. That answer is now your new input that you're going to put into g of x. Okay, so let's first find f of 4. So f of 4 is equal to 3 times 4 minus 14. There's 12 minus 14 is negative 2. Okay, so now that my original input was 4, it outputted to negative 2. Now I'm going to take that negative 2 and I'm going to stick it into the g of x function. So g of negative 2 is equal to negative 2 squared plus 5. Okay, so then that's 4. I was trying to add the whole thing together in my head. Anyway, that's 4 plus 5, we get 9. So g of f of 4 is equal to 9. So let me talk to you about the domain thing that we were looking at before on this very, very simple case here. The original input came from the interior function, right? I'm going to stick 4 in there. Its output came from the range of f of x. Its range was negative 2. That has to be in the input. It has to be in the domain of g of x in order for me to be able to use it. In this case, it was all real numbers, so I didn't have to worry about anything. Okay. So let's f of x and g of x equal those two functions that I just gave you. Find these compositions and then state the domain. So first one, I'm finding f of g of x. Ooh, look, this is a little bit backwards from what we were looking at before. G of x is the interior function. It's going to go inside the x on f of x. So I have 6 on the outside. On the inside, instead of having the x on f of x, I'm going to stick in 4x plus 5, and all of this raised to the negative 2 power. So let me write this in a way that we've seen before, something like 6 over 4x plus 5, all of this squared. So here is our new composed function, right? I took g of x and I stuck it in for x and f of x. Now let's talk about the domains of each of these. Okay, so the domain, well actually we're going to have to talk about domain and range. So the domain on this is essentially 6 over x squared. 6 over x squared, whenever you go to graph this, it has a vertical asymptote at 0 at the y-axis. And since this is like even multiplicity, the graph goes like this, and up and up. So anyway, its domain is everything except 0. And its range is everything bigger than 0. So y is greater than 0 because it has a horizontal asymptote at 0. Okay, and now for this function's g of x's function's domain, it's all real numbers because it's linear and its range is all real numbers. Okay, let me switch colors here and go. Now let's talk about the domain of it. The interior one is g of x. So I would say that the domain should be all real numbers for this function right here, as long as this is completely inside that. But it's not. It's not because I'm leaving out 0. So I need to go back and see, oh, what is it that makes this thing equal to 0? And that's exactly what we do whenever we were trying to find the domain of rational functions. We took that bottom and we're like, oh, 4x plus 5, that cannot be equal to 0. And so x is not equal to negative 5/4. So there's the new domain. And that's something that we've looked at before, but here's a new way of looking at it in terms of composition. Okay, so let me switch colors again, get all kinds of colors up in here. How about green? This time we're going in the opposite direction. We're going to stick this in there. G of f of x. So the exterior function this time is the 4 times, this opens up a little hole, and in the hole I'm going to put 6x to the negative 2, and then plus 5. Okay, and then simplifying it, I just go ahead and multiply. I get 24x to the negative 2 plus 5, which is 24 over x squared plus 5. Okay, and then whenever I go to find its domain, now this one's in the opposite direction. We would say that the domain of h of x, which is this new function here, should be the domain that I put in green there, which is the interior function, x is not 0, as long as its range is completely inside the domain of the exterior function. Y is greater than 0, that's completely within all real numbers. So this means that the domain is just x is not equal to 0. And if I just took that function by itself, that would make sense. X can't be equal to 0. Okay, let me see. I think we're going to look at one more, and this one may, just maybe, might blow your mind. Just a little bit, just a little bit. Switch this thing back to red. Well, not that red, this red. Right here. Okay, so we're going to find this function f composed with g of x. Which one is the interior function? The one that is closest to the x. So this square root thingy is going to go inside the squared. Hey, that's kind of convenient because they're going to cancel each other out, right? So f composed with g of x is equal to the square root of 9 minus x squared, all of this squared, and then minus 9. Now let's simplify it. So the squared and the square root will cancel each other out, and I would have 9 minus x squared minus 9. Now the 9's cancel each other out, and I have just negative x squared. So let's call that h of x. There's my answer. There's my composition of these two functions. And you know, like we would go, if that's the function I'd have, it's just negative x squared, I'd go, that's all real numbers. I'd go domain, all real numbers. But it's not. We switch colors. Switch, switch, switch. No, it's not that button. It's this thing. Blue. Cross this thing out. We need to go back and look at the original one's domain and range. So you need to take the domain and range of the interior, both of them. So here's the interior function. So for g of x, its domain. Whenever I look at the square root thingy, remember this is 9 minus x squared has got to be greater than or equal to 0 since it's a square root. And then I make that an equation. I can't solve the inequality with a squared in it. Add the x squared over, take the square root, plus or minus 3. And that goes on a number line. So I have 0, 3, and negative 3, and they get colored in. Now which thing works in there? Does 0 work? If I put 0 in there, 9 minus 0 squared, that does work. It gives me real numbers, so it's everything in between negative 3 and 3. Okay. For its range, just think about this for a second. What's the smallest thing that I can get from this? The smallest thing I can get from this is if this and this were equal, so they'd cancel each other out. Like if that's equal to 3 or negative 3, I'd have 9 minus 9, so it would be 0, and it can be equal to 0. Okay? And then the biggest it can be is if this thing is just 0, and then 9 minus 0 is 9. Square root of 9 is 3. So that's our range. If you have trouble with the range, you could just graph that in the calculator and then try to figure out what like lowest to highest point is. Okay, now f of x, its domain, that's what we need to examine. Its domain is, since it's quadratic, it's just all real numbers. Okay, and so we go like this. The domain of h of x should be the domain of the interior function as long as its range is completely inside the domain of f of x. Is from 0 to 3 within all real numbers? It is. This means the domain is only from -3 to 3. And that is kind of peculiar, because if you look at that equation, you're going, it's all real numbers because it's just quadratic. But it's quadratic only because it's simplified like that. The original one wasn't like that. Let's look at
this on the calculator. So if you just pull this up on the calculator and you type that in exactly before we simplified it, so in the parentheses you have the square root of 9 minus x squared, all of that squared minus 9, and now you hit graph. Let's go to zoom standard, which is 6. And it looks like the parabola as you would expect to see it. It's just negative x squared, which is upside down from the origin. But look, it doesn't exactly go. It doesn't keep going down past there. It doesn't go to the edge of the screen. Just to demonstrate this, let me go down here, and let's make this go from 0 to 20 instead. And make that scale 1. That's fine. Well, no, 0 to, actually, -20. There we go, to 0, maximum. Now let's hit that graph. Oh, that was on the x's. Oh. All right, go back to the window. -10 to 10, and this should be -20. Come on, to 0. Now let's look at that graph, and I can see definitely it stops, right? It doesn't keep on going forever. If I look at this, it begins at -3 and ends at +3 right there. So there you go, some graphical
proof of this. Calculator does understand it a little bit. Okay, in the next video, there's going to be some exercises for you to practice on your own in this thing called decomposition.